I'm Rachel Winheld, and on behalf of Science at Cal, it's my great pleasure to welcome all of you to the Science at Cal lecture today. It's always great to see familiar faces, and we have a lot of new people here in today's audience, so welcome to all of you. I know we have some students from visiting the Berkeley campus this summer to study computer science from high schools all across the U.S., and we're really thrilled that you could join us here today. And I know that one of my colleagues in the physics department is bringing some young members of her family to the talk today. So everybody, welcome to today's lecture. If you are new to this lecture series, or you're not yet on the Science at Cal e-list, but would like to stay informed with occasional notifications about this lecture series and other activities going on through Science at Cal, please go to our website, scienceatcal.berkeley.edu. I welcome you to visit the site and sign up for the list. I also like to mention that while you're there, you can click on Support Science at Cal, and if you're so inclined, large or small donations from people like you are incredibly important to us to help us maintain and grow our programs, as well as let our administrators and our science policymakers know that you value this kind of opportunity. So just a couple of announcements before we get to today's talk. If you're going to be around in August 18th is the next Science at Cal lecture. Our speaker will be Dr. Anton Trenzin. He is with the Experimental Astrophysics Group at Space Sciences Laboratory, and I wrote down the title of his talk because it's a good one. Can one see a flower through a granite wall? Amazing capabilities of neutron imaging. So mark your calendar for that one. And later in the fall, October 3rd, we're already putting the word out that Nobel Prize-winning physicist Adam Rees of Johns Hopkins University will deliver the Distinguished Lecture in Astronomy. That will be in the Bechtel Engineering Center, and of course we'll be announcing it as the date draws closer. And of course his topic will be how supernova reveal the expanding universe, the accelerating universe. But we don't have to wait for October, because as you know, today's lecture, which will be delivered by Dr. Jeffrey Silverman, is going to inform us about these exploding stars and the runaway universe, and dark energy and the runaway universe. So the good news is that we have Jeff with us here today. He will be leaving Berkeley soon to assume a postdoctoral position at the University of Texas at Austin. He's been studying and observing supernova here with Professor Alex Filippenko, and we're very lucky to have him. So please join me in welcoming Dr. Jeffrey Silverman.
All right, good morning, everyone, and thank you, Rachel, for that very lovely introduction. So, as Rachel said, I'll be talking about exploding stars, known as supernovae, dark energy, and the runaway universe. I've been here for almost 7 years now, working with Alex Filippenko. Many of you might recognize him. He's on TV a lot. Here's us from graduation last year. If you watch The Universe on the History Channel, he's in there a lot, and I'm in the background in a few episodes. So. There's my plug for my TV career. Okay, so what is a supernova? Let's start off with some basics, folks. The plural is supernovae, sort of a Latin bastardization. I'll sort of switch between the two. They're bright and powerful explosions of a star, the death of a star. Some of the biggest explosions in the universe. The speed of the material exploded outward can reach something like 20% the speed of light, the speed of light being the fastest speed in the universe. A single star exploding can outshine its host galaxy, which is made of hundreds of billions of stars. And in about 1 month, one of these supernovae can emit as much energy as the entire sun will in its 10 billion year lifetime. So the name nova is Latin for new. I don't know much Latin, but I at least know that one. It was first used by some of the Renaissance astronomers to describe new stars that popped up in the night sky. The prefix super we sort of added on in the 20s to distinguish them from what we now call classical novae, sort of smaller, weaker cousins of the supernovae that I'll talk about. So I won't talk about classical novae today. I'll talk pretty much all about supernovae. Whether or not humans knew it, we have been observing supernovae for about 2,000 years. I'll show some historical records of people seeing supernova, not knowing what they were until maybe about 100 years ago, but seeing them and pointing them out for the last couple of millennia. And the term supernova was coined by a Swiss astronomer named Fritz Zwicky. He worked at Caltech for most of his career. He was sort of a funny, curmudgeonly looking guy. He was known to call people spherical bastards because they were bastards any way you looked at them. Sort of one of the people I model parts of my personality after, if you know me. Okay, so onto some pretty astronomy pictures. Any good astronomy talk should have lots of pretty pictures in it. So this, as many of the amateur observers in the crowd know, is the famous Crab Nebula. This is a picture using the Hubble Space Telescope. And so when a star explodes, it gives off a lot of energy, a lot of material gets blasted away from the star. And when that material from the exploding star runs into the gas and dust that was sort of just minding its own business sitting around the star before it exploded, it heats up. And when gas in space heats up, it starts to glow. And so this is from a supernova that went off in the year 1054, so almost 1,000 years ago. And what we're seeing here in the modern day is the gas and material that blew away from that star running into the surrounding material. And when that crash happens and it lights up, we call it a supernova remnant. So I'm starting sort of at the end of the supernova. After it's been exploded, after about 1,000 years or so, we'll see this remnant. And so I said the supernova went off in the year 1054, and it was recorded by everybody that was in the northern hemisphere that was looking at the sky, from Asia, North America, parts of Europe, but they had some dark age kind of issues at the time, but we think there might be some records there. But pretty much around the world, people saw this. It was bright enough to see in the daytime for almost a month, so a brand new star that was bright enough to see during the day for almost a month. That was really freaky to a lot of people back then. It'd be really freaky to us now, for the most part. And it was visible well before the telescope was invented. So by just the naked eye at night, it was visible for nearly 2 years. So here is one of the earliest records, perhaps the earliest record of a supernova. This is a petroglyph from New Mexico. The Anasazi Indians made this in the year 1054. And sure enough, if you go to New Mexico and you look this direction and you take a look and you figure out when we think the supernova went off, here's a picture of the supernova. Here's the moon's relative position and the phase, so it was a nice little setting crescent there. And then the artist put his hand up there to sort of give you a size scale to figure out what the distances between these two are. And that seems to be correct. We're pretty sure that this is a petroglyph of the 1054 supernova that gave us today the Crab Nebula. Luckily, we've come a little bit forward in technology in the last 1,000 years. It would be hard to write a supernova thesis if all I had was rock drawings. It would also be a much heavier book. My thesis is already pretty heavy, but... Okay, so skipping ahead a few hundred years to another interesting character in the history of astronomy, Tycho Brahe, famous Danish astronomer, observational astronomer, basically with just his eyes. He found a supernova in 1572. Sort of, again, just cataloging all the stars out there, and then saw a new supernova, or a new star appear in the night sky. This guy has a lot of quirky stories about him. My favorite one I like to tell is he was apparently a hothead, and in college he got into a lot of fights and duels, and in one duel he got his nose cut off. But he was wealthy enough and was endowed by the local princes enough where he got a gold and copper plated nose put in. Either this was probably before this painting was made, but I assume he paid the painter enough to make him look pretty. So. Yeah, interesting character. And here's what Tycho's supernova looks like today. About 500 years later, again, we have a supernova remnant where there's gas and material running into sort of the surrounding ambient medium around the star that exploded. This is actually an X-ray picture. This is not the visible light we see with our eyes. These are X-ray light, the same kind of X-ray light that you deal with at the dentist and when you break a bone and you go to the hospital. But we have a space telescope, we have a few, but the big one, and the one that this came from, is called the Chandra X-ray telescope, a NASA satellite that's in space, taking pictures at X-ray wavelengths. And then the colors basically correspond to the energies of the emitting material. So the blue is the highest energy, the red is the lowest energy in this X-ray region. And again, you can see it's sort of clumpy. It's quasi-circular, which is what a sphere looks like on the sky. So sort of blew up in a sphere like you might imagine. There's some little clumpiness, which tells us about the material around the star. And I'll talk a bit more about that in a few slides. All right, not to be outdone, Tycho Brahe had a grad student, very famous astronomer, named Johannes Kepler. Well, he didn't want his advisor to get all the credit, so he went out and found a supernova about 50 years later. I think we should all aspire to find as much stuff as our advisor has found. So I've got some work to do, but working on it. All right, so Johannes Kepler, German mathematician, astronomer, geometrist, all kinds of cool stuff, found a supernova by eye in 1604. And this is what the supernova looks like today. This is Kepler's supernova remnant. Similar to what Tycho's remnant looks like. Again, this is an X-ray picture. The colors mean the same thing, the energies. Similar, not quite the exact same. This one's about 50 years younger. We can see how they age. The area around the star, the ambient material around the star is different in these two supernovae, but vaguely similar. And this is the last supernova that we're sure happened in our own galaxy. So basically, for the rest of the talk, I'll talk about supernova, stars exploding outside of our Milky Way galaxy. This is the last one in our galaxy. There's maybe a couple we're not totally sure about, but this is definitely our own galaxy and the last one that we saw 500 years ago, give or take, 400 years ago. All right, so way back in 1987, hey, remember the 80s? A supernova went off in a very nearby galaxy, something called the Large Magellanic Cloud, sort of our backyard neighbor galaxy, a very tiny thing right near the Milky Way. This is a very close by galaxy, very well studied. We had pictures of it, and we could see this kind of big star. And then in February of 1987, it went supernova. It exploded. And so this is in our cosmic backyard, a mere 170,000 light years away. My dad always asked me to put these things in miles, so it's a 1 with 18 zeros miles, a billion miles, for whatever that's worth. I don't know. He seems to think that that makes sense to him more than 170,000 light years, but okay. So this exploded in 87. It's over 25 years old. People are still observing this today, mostly with big space telescopes. But people are still working on this object because it's so close we can observe it basically for decades. So this was really cool. People did a lot of work on it back in the 80s, through the 90s, even through today. Here's a time lapse of images from the Hubble Space Telescope of this supernova. And so what we're seeing here is the birth of a supernova remnant. We're seeing the beginnings of the junk that was blown out from the central star, which blew up in the middle, running into all this junk around the star that was just sitting there. And we can tell that that stuff is very clumpy. You see all these bright spots popping up, getting bright. That's a really dense cloud that the shock wave and the material's running into. The parts where it's darker, there's maybe not as much stuff. And so this is teaching us about what was around the star when it exploded. And again, a baby supernova remnant. Now on to a slightly more recent supernova. This is from 1993. And this is also the birth of a baby supernova remnant, a little bit younger than the one from 87. This is from 93. And now these are radio images. So I'm kind of jumping across the electromagnetic spectrum. So radio waves, just like what we pick up in our radios, okay, that is an outdated statement, but radio waves and various kinds like that, microwaves are part of the radio spectrum. And again, the colors map to sort of temperature and energies. And again, the supernova went off, and this time lapse shows this ring of material as it hits other material, lights up, gets hot, and again, birth of a supernova remnant. Feel free to come down. There's room in front. I don't mind. Please sit down. I don't want you to have to stand the whole time. I'm the only one who have to stand the whole time. Okay, so back to the optical, visible light that we see with our eyes. This is the kind that I mostly work on. I'll basically be showing only optical images from the rest of the talk. Here is one of the classic supernova pictures that you might have seen before. I like to use it on posters. It's pretty. And here is a very good example of how bright these stars can be, how bright these exploding stars can be. So here's a spiral galaxy, very similar to our own Milky Way. You can see it has a bright core of stars, maybe a billion or a few tens of billions of stars in the middle there. It's got these dark dust lanes and brighter spots that make up the spiral arms. We're sort of seeing it edge on. If we saw it face on, we'd see the nice spiral structure that you guys always hear about. But we're sort of seeing it tilted. And this is one single star in that galaxy that has exploded. It's gone supernova. And you can see the brightness of that is about the brightness of that. So one star is about as bright as a billion or tens of billions of stars in this host galaxy. And that was a Hubble image. And now we're going to an amateur astronomer's image. So this is someone who looks for supernova. There's hundreds of amateur astronomers around the world that look for supernova and take pictures of pretty galaxies that are nearby, backyard telescopes, usually a dark site, not really the Berkeley, Oakland area, but sometimes you can do some good stuff there. And so here again is our spiral galaxy, a different one. It's got a bright core. It's sort of got, you can't see the arms or the dust lanes as well because it's a lower quality image from a smaller telescope. But this is a nice time lapse of a supernova. It gets bright and then sort of fades away. And that's basically what the supernovae look like in most of our observations. A bright spot pops up and then fades away. That was going to be my next statement. Very good. So this entire movie lasts about 4 months. And that's vaguely typical, sort of the 4, 5, 6 month time scale for it to pop up and then fade away. Some supernovae, if they're closer, if they're special kinds of supernova, we can see for years, decades, if they're really close by and if we use some of the biggest telescopes in the world. But sort of your average run-of-the-mill supernova with your average research telescope, you've got a few months to watch it, and then it's pretty darn faint. OK, and now this is not quite as pretty as a picture as some of the Hubble ones, but this is a really cool one. This is an interesting science result. So here is a picture from 2005 from a European telescope. It's a bunch of stars, sort of a zoom in on a nearby galaxy. And we can immediately see the stars have different colors. If you go outside and look carefully at the stars, some are kind of reddish, some are kind of bluish, some are kind of whitish. And the color tells us about the temperature. The blue-white guys are hot, and the red-orange guys are cold, and the yellow guys, which are sort of like the sun, are sort of in the middle. And so we have all these different kinds of stars. They're all different colors. Great, wonderful. 2008, a supernova goes off. Hint, it's right where these yellow crosshairs are. But a supernova goes off in 2008. These European astronomers that took this picture went back in 2010, took the same picture of the same stars, and there we go. The star is gone. So let's do that again. So 2005, then 2008, a supernova goes off. 2010, they go back. All the stars are there, except where the supernova was. So we watched this star blow up, and now it's gone. In theory, there is a supernova remnant there, most likely, because we know that supernovae make these remnants. But it's so much fainter than the supernova itself that we really can only see the nearest by remnants. And this guy, even though it's very close, is probably, we're not going to be able to see that remnant. It's probably going to be too faint. But it went away. And there's only a handful of cases, maybe 8, 10, depending on who you believe, of seeing a star, seeing a supernova, and then not seeing the star anymore. So you have to have really close by galaxies, really accurate precision, really precise measurements of where the stars are. And it's only been done a handful of times. Our group at Berkeley has done this for a handful of stars. I mentioned this was a European team, sort of our main competitors in this subfield. But I will give them props, because this is really cool pictures I like to show. OK, now for some words. Why should we care about supernova? I showed you a bunch of pretty pictures. That's lovely. That's nice. But why should we care? Well, these are hugely powerful explosions, much bigger and much more powerful than really anything that we can study on Earth. So the extreme conditions in the explosion and how these stars are dying, how are they born, how they evolve, and how do they die, is all intimately related to these explosions. And so we can test our models and ideas on how stars evolve. The massive stars, some of the massive stars make supernova. I'll talk about that in a second. White dwarfs, I'll also mention, a compact dead star. We don't really know a lot about those. We can learn a lot through supernova. And then how these things explode, the physics of the explosion itself, the nucleosynthesis, the building of new elements. I'll talk a bit more about that as well. Most of the elements on the periodic table come from supernovae. It can trigger star formation. I talked about a lot of the gas and material running into clouds and making pretty supernova remnants. But there's also energy blown out, this blast wave you see in movies of bombs exploding. And that can sort of shake up a nearby gas cloud. And when you shake up a nearby gas cloud, it might start to gravitationally collapse on itself. And that's how new stars are born, from these clouds collapsing on themselves. So you have the death of one star triggering the formation of new stars. It's a very circle of life. I'm a big Disney fan, so I like to mention that. You also disperse these elements. I'll talk a lot more in a few slides about building up new elements and then dispersing them out into space. We would not be here without supernovae. The Earth would not be here without supernovae. And so I'll get a bit more into that in a handful of slides. And then the last point here, tracking the expansion of the universe, getting into the dark energy, the runaway universe stuff. I'll sort of end with a few slides on that. OK, so how do we make a supernova? Well, here's my cartoony picture of one of the ways to make a supernova. Here's the sun, sort of to scale. Here's the Earth, sort of to scale. And here's this thing called a white dwarf. So a white dwarf is you take the entire mass of the sun and you cram it down into the size of the Earth. So it's extremely dense. The sun will turn into a white dwarf in a few billion years, 4 or 5 billion years. Basically what happens is the star stops doing fusion, which is how you produce energy in a star, and its outer layers sort of float away, and you're left with a very dense, hot core, mostly made of carbon and oxygen. And that's what we call a white dwarf. Now, how do you turn a white dwarf into a supernova? How do you blow it up? Folks in the back, there's still seats on the side and in the front. Feel free to come down. So here's how you turn a white dwarf into a supernova. Specifically, the naming conventions are awful. We can talk about them later if you're really interested. But a type 1a supernova. You have a white dwarf, and it needs a friend. It needs a binary companion, a partner. About half the stars we think in the galaxy have binary companions. The sun does not. It is a single star. So I said the sun will turn into a white dwarf eventually. It will never go supernova because it doesn't have a companion. OK, good. We're safe from that. How do you get a 1A supernova? You have a white dwarf, you have a companion star, and they're close enough so that the gravity of the white dwarf can actually siphon off some material from its companion star. And one of the wacky things about white dwarfs, something that was discovered by an Indian physicist, Chandrasekhar, back in the early 20th century, is that there's a maximum mass. White dwarfs can only be about 1.4 times the mass of the sun. Anything bigger, and it has to collapse on itself. It just can't hold itself up at that point. So you have a white dwarf. It evolves. It's born. It has a solar mass, 1.2 times the mass of the sun, something like that. And it has a nearby partner. It starts siphoning material. Eventually, you might build up enough material on the white dwarf where it hits this magic Chandrasekhar limit of 1.4 times the mass of the sun, and then it has to collapse. So you add on material. It builds up. It builds up. It hits that magic limit, and then, woot, you have an explosion. And it's a runaway thermonuclear explosion. You're basically setting off a hydrogen bomb, really it's a carbon-oxygen bomb, that weighs the mass of the sun, a little bit bigger than any H-bomb that we've built. So this is a huge explosion. It releases a ton of energy, and there's nothing left. The supernova goes, the star explodes, it fuses up to higher and higher elements, and you have no remnant left. There's nothing left. There's gas and material that are spewed out, but at the site of the star, there's nothing. It's been completely blown up. The other main type of supernova I want to mention is the type 2. Now, the type 2 come from very massive stars, maybe 10 times the mass of the sun or heavier. And what stars do to produce energy, they fuse hydrogen into helium. That's what the sun's doing. It's basically what it's going to do its entire life. More massive stars can fuse up to higher elements. And in fact, here's sort of the chain, helium to hydrogen to helium to carbon, neon, oxygen, silicon, all the way up to iron. And so what we have during the star's lifetime is you have fusion in the core. These things are getting fused and producing energy, pushing outward. And then you have gravity pushing down on all of these other outer layers. And so you have stuff pushing down, stuff pushing out. You're nice and balanced. The problem with iron, when you get up to iron, fusion doesn't work anymore. You can't fuse iron and get energy out. So if you start fusing up to iron, you get this big iron cannonball in the center of your star. You no longer have stuff pushing out because you're not doing fusion in the middle, but you still have gravity pushing down. And so I've got my fun little demo today, where the ground is our iron core. Sort of the baseball is the mid-range oxygen and silicon, and then my ping pong ball is the light outer layers of hydrogen. So normally everything's nice and stacked up. This would be sitting on the ground, or a bunch of stuff here. Fusion, pushing upward, gravity, pulling downward. Then you get to iron, no more fusion down there, but you still have gravity pulling down. Well, if you have gravity pulling down and nothing pushing up, what happens? Oh, I totally failed. All right, let's try this one more time. I totally practiced this yesterday, too. There we go. So if I just drop the ball normally, it doesn't bounce very high. But if you have stacked layers of material with the lightest stuff on top, you can launch the top light stuff pretty far. And so the collapse and then bounce off of the iron core is what gives us a supernova. The lighter layers will fall down, hit the iron core, bounce off, and explode. And that's how we get the core collapse, type 2 supernova. OK. So not only do we have all these elements being made in the star, basically the carbon up to iron, that's the only place in the universe you make these elements. They don't occur naturally anywhere else. They're just cooked up in stars. Without supernovae, they would never get blown out. Yeah?
What about the rest of the elements?
Great question. I'm getting there in 2 sentences. These would be stuck in the star forever if there wasn't a supernova. So the supernova releases these elements. Now, the elements on the periodic table from iron to about uranium are actually made in the supernova explosion themselves. There's so much extra energy around in this kind of supernova and the other kind that you can actually fuse heavier than iron, which does take an input of energy, but there's enough around where you can make elements all the way up to uranium or so. Anything heavier than uranium is mostly made in particle accelerators and fancy labs like at Berkeley Lab and Fermi Lab and places like that. All right, so good. OK, so on to how do we find these supernovae? I told you some really cool stories. People in the back, there's room, I promise. Come down and take seats. They look so sad back there standing up. So we think about one supernova goes off per second somewhere in the universe. Now, most of these are so far away, so faint, that we're just never going to see them. But we think about one per second in the universe or so. From the late 90s to sort of the late aughts, that's what we're calling the zeros now, right? The aughts. late 90s to the late aughts, we found about 1 to 3 supernova per day from Earth. Now that was mostly about half amateur astronomers and about half some of these early surveys that are looking specifically for supernovae. And I'll talk about the one that our group has run in just a minute. But our group started its supernova search in 1997 and was basically the leader of finding supernovae as far as professional astronomers go for about a decade in there. Since about 2009, we've bumped it up to about 5 to 10 supernovae per day. And that's because we've had new sort of second-generation supernova searches come online with bigger cameras, bigger telescopes, more sensitive cameras, better software to find supernova. It's not an easy game. I'll show you a couple pictures in just a minute here. And so we've sort of bumped that number up a little bit. And sort of the next generation, looking at 2015 and 2020, this number could easily double again, maybe go up to hundreds, depending on what kind of funding actually gets passed. And then just for a ballpark, 1 supernova per galaxy, that's kind of like our Milky Way, about per century. That's sort of the ballpark number we like to throw around. For those of you keeping score, we haven't had a supernova in our galaxy for about 400 years. So we're a bit overdue. And if I have a couple minutes at the end, I might talk about some stars that could go supernova in the near future in our galaxy. So if there's only 1 supernova per galaxy per 100 years, that would take me quite a while to write a thesis. However, you can sort of respin that and say, well, it's 1 supernova per 100 galaxies per year. OK, I've been in grad school for 7 years, or I was in grad school for a little over 6 years. That's only 6 supernovae. That's starting to get a little bit ugly. I can do a little bit, but not much. But if you start looking at tens of thousands or tens of thousands of galaxies per night, then you can start building up a good sample of supernova. So the game for supernova discovery is look at as many galaxies every night as possible and try and find that 1 supernova per century that pops up in one of those thousands and thousands of galaxies. And that's exactly what these supernova searches do. This is KATE, the Katzmann Automatic Imaging Telescope at Lick Observatory, just south of here near San Jose, in the mountains just east of San Jose. This is a telescope that was built by my advisor, Alex Filippenko, and run by our group since 1997. You know that it's a Berkeley item because of the Cal colors, go Bears. And to prove that I've been there and ruined one of the pictures at night, there's me on an observing run wandering around the summit of Lick Observatory. And so KATE is fully robotic. No one goes to the telescope to look at it. I just go to take pictures usually. Nobody's controlling it. She has weather sensors. She knows when it's nice out. She knows what galaxies are up that night. She knows when sunset is. So if it's clear out, if it gets dark, she opens up this dome slit and then starts taking pictures of galaxies that are up. And she has a preset list of galaxies, and she compares them, the new pictures of galaxies, to old ones. And if there's a new bright spot, that might be a supernova. So here's one of the first supernova that KATE ever found, the 8th discovery, according to my notes. So here is sort of a low-quality-ish picture of the host galaxy from before the supernova. KATE takes a new picture, gets this picture, and says, hey, I see a new supernova, and then emails us, and then we might go follow it up with other instruments. So hopefully everybody has spotted the supernova. I started with a softball here. Yeah, there it is. OK, so that one's easy. We could have done that fine. But you're taking thousands of these images a night, and a lot of them are not nearly as easy. Here's a very pretty one. This is a supernova that was discovered last August in the Pinwheel galaxy, M101, for those who know it. It's easy to spot where this galaxy is. It's just above the handle of the Big Dipper. You need a moderate-sized telescope to see any fuzz, but you can sort of see the part of the sky where it is right above the handle of the Big Dipper. And so here's the before picture. This is with Hubble. So it's nice and detailed, really faint stuff pops out. And then here's the after with the supernova in it. And that's actually taken from a small telescope in Santa Barbara. So that's why it doesn't look as pretty, as bright. But if you match up all the bright spots, there's going to be one extra one in this picture as opposed to that picture. And that's our new supernova. Now, there's a lot of dots, but this one is still pretty bright, pretty obvious, fairly straightforward. There it is. All right, so I saw people pointing, and good. A few people got it. Excellent. This actually was not found by KATE. This was found by a collaboration called the Palomar Transient Factory. It's an international collaboration of astronomers, many of which are at Berkeley and at the Berkeley lab, so we're very proud of this one. And this was found very young. It was a very interesting object. We wrote lots of papers. We're still writing lots of papers. We had some YouTube videos that got tens of thousands of hits talking about how this was really cool and interesting and got so bright you could see it in a backyard telescope, this actual supernova, which that was the first time I'd done that. That was pretty fun. So here's a bit tougher image that has a supernova in it. So again, here's the new image from KATE. Here's the template old image. And then when you subtract them, we can run our code that sort of subtracts pixel by pixel and figure out, oh, look, there's an extra bright spot in the middle, and that's a supernova from 2001. Some things don't subtract exactly, and you get little weird residuals. There's one pixel that's really bright because it got hit by a high-energy particle called a cosmic ray. So you have to be smart. Your code has to be smarter than just subtract the two, and anything that's left over is a supernova. That would be bad. We would have a lot of garbage. So we're getting better at writing the code. Kate had some very good code. This Palomar Transient Factory has even better code, developed by some of the people, in fact, in this room, perhaps, and a lot of people around Berkeley and LBL. And if you look closely, you might be able to convince yourself there's a little tail of extra dark emission right there versus right there. And so, yeah, all right, there's a supernova there, but I certainly would not be able to see that just kind of glancing through thousands of images per night. So luckily, our computer code is good enough to do these kinds of subtractions and find these supernovae. So here is the stats for the Lick Observatory supernova search. I mentioned we started in 97. The first object we found was 97BS, a supernova from sort of March, April, something like that, well before I got here. Oddly enough, my advisor likes to point out that in hindsight, we don't think 97BS was actually a supernova. We think it was an imposter supernova, not quite the same thing, which he said was appropriate given its name. We found a lot of supernova through the 90s and early 2000s. We set a lot of world records, and we've been slowing down the last couple of years as these new collaborations like the Palomar Transient Factory have been finding way more than Kate ever could. And so we sort of switched the strategy on what Kate finds and how she finds things to go for very specific science goals. We used to be just, let's find as many supernovae as possible. The Palomar Transient Factory and some other ones are doing very good at that now. And so since we control Kate ourselves at Berkeley, we can tweak things to find very specific kinds of supernova in a very specific way. And so, we sort of tailed off the last couple of years. This year, we've only found 6 so far, but they were very young. They were for very specific science goals. So, sort of switching. You got to evolve or go extinct, as Alex likes to say. And you can keep track of all of our discoveries are on the website. They are all public immediately. Here's the latest Kate discovery. Not the prettiest picture, but this is real data. This is what comes out of the Kate telescope. This is the supernova on top of a very faint host galaxy, so you can't even really see the galaxy underneath. Most of these dots are stars that are sort of in the line of sight. That's probably a galaxy, a big galaxy that's kind of far away, unassociated with the supernova. We've got a sense of scale and direction. S1 is just sort of to tell us if we find that star, we can jump over to the supernova. This was discovered last May, and it's a type 2. So this was one of those massive stars that had iron in the core and collapsed on itself and then bounced and exploded. So real data from our telescope. So I want to show not only just real data from the telescope, but real processed data, graphs, plots, figures. I'm a scientist. I'm going to make you guys look at graphs. So here is what's called a light curve of a supernova. And it's simply how bright is the supernova versus time. So we have days since discovery on the bottom versus brightness. And the different colors are just different filters. For those that know your optical astronomy, we've sort of got BVRI, or BVRI that way. The supernova gets brighter and then fades away. And you can see the different colors have different shapes. And again, that tells us stuff about the energy in the explosion, the temperature, how far away it is, because we can compare it to other ones that we know about. So you can get a fair amount of information. However, I specialize in listening to Pink Floyd. No, I specialize in what this image, which I love showing this because I like classic rock, and I do spectroscopy. And so this is, you send white light through a prism or some kind of dispersive optical element, and you break it up into the rainbow. And so all of you are spectroscopists. You have all done spectroscopy. How many people here have seen a rainbow? Congratulations, you're all spectroscopists. A rainbow is simply water particles, water molecules in the air, acting as a prism or a lens and splitting the sunlight into all the component colors. That's spectroscopy. Now, instead of using sunlight, I use supernova light. And instead of using a simple prism or a water droplet, I use big, crazy instruments with all kinds of junk going on. But it's the exact same principle. And so what can I do with my spectra? Well, I have to make plots. I have to make graphs. So here is sort of a continuous spectrum like what you might see in a normal rainbow with your eyes. And if I plotted the brightness versus wavelength, now remember wavelength is another fancy astronomy science word for color. Basically, it's the same thing. But we can put a very specific number. I can say a very specific number is a wavelength, and it corresponds to sort of a color. But to be more precise, more accurate, we can call it a wavelength. That's fine. So continuous spectrum, basically all the colors are the same brightness. It's a nice flat line. Great. We can also get something called emission lines, where most of the stuff is black, but at very specific colors or very specific wavelengths, you have a big spike. It's very bright. And so we have mostly flat with some bright spots. And the exact opposite case can occur as well, absorption lines, where it's mostly constant, mostly bright, but at very specific colors or wavelengths, you have an absorption, a drop in the brightness. OK, so now if I do that to supernovae, here's what I get. Here's a spectrum of a type 2 and a spectrum of a type 1a, where we have wavelength versus brightness. To give you an idea of colors, the sort of blue that we would see is here to green to reddish. Blue, green, red. The stuff over here is actually ultraviolet, and the stuff out here is actually infrared. So the data that we get covers not only the part we can see, but a little bit of extra on either side. The UV that burns our skin, and the IR that's basically heat vision. And what's cool about these spectra, not only can I figure out temperatures and energies, I can figure out the velocity, how fast is the material moving out in the explosion. I can also figure out something very important that I referred to earlier. I can figure out what elements are in the supernova. And that's because a couple hundred years ago, scientists figured out every element on the periodic table has a very distinct spectrum. And we can use them like fingerprints to figure out what elements are in the supernova. And so these bumps and wiggles, and that is a technical term, I can look at these bumps and wiggles and tell you which bump and wiggle corresponds to what element. So the type 2s have these big hydrogen features. H alpha and beta are two different hydrogen lines. Calcium, oxygen, and iron, a little bit of iron. The type 1As have oxygen and calcium, this big silicon feature, sulfur, iron, magnesium, all kinds of good stuff. And so I can use my spectra to figure out what elements are in the supernova. And again, that's where most of the elements on the periodic table come from, our stars, and in the explosion. OK, so now on to how do I get these observations, some pretty telescope pictures. This is the 3-meter telescope at Lick Observatory. When astronomers talk about the size of a telescope, they'll quote some distance. And that is just the diameter of the biggest mirror or lens, which for this telescope is back here. So that's about 3 meters across, about 10 feet across. Again, to prove that I've been there, I've spent many, many nights up there. There's me ruining one of the exposures, I'm sure, but that's fine. I was observing. It's fine. No big deal. These are the famous twin Keck telescopes on the dormant volcano in Hawaii, Mauna Kea, on the Big Island. These are 10-meter telescopes. You can't see the primary mirror. It's down here. Sort of it's about this distance across. That's about 10 meters, or 30 feet. To give you a size scale here, I like this picture because that's a full-size SUV in front, which is pretty impressive. And then I got to visit the summit last summer for the first time. That was pretty cool. Took pictures. There's me. Notice I'm wearing jeans and a big parka. It was 80 degrees at the beach when I started driving up the mountain. Then you get up to 14,000 feet, and it's cold, and you want a parka. And then, of course, the Hubble Space Telescope. And unfortunately, I do not have a picture of myself near it. A few years ago, I would give the joke like, oh, I've always wanted to be an astronaut, which is true, and I always wanted to go up and fix the Hubble, but now NASA's definitely not going to fix that. So I need a picture of like the James Webb Telescope with me floating next to it or something. But that's for another talk in a few years, perhaps. There's no SUVs or people to give you a size scale, a sense of scale here. So I do like to remind people this thing is about the size of a school bus. So it's pretty big, but you rarely get to see a good scaled image. So this is the size of a school bus, and we use this one as well to get to discover supernova and to follow up supernova, get spectra, and make these light curves. And these are, well, actually this is one supernova from 1997, discovered by the Hubble Space Telescope. And the way we use Hubble is the exact same way that Kate finds supernova, the exact same way that the Palomar Transient Factory finds supernova. It takes a reference image, it goes back a few weeks later, takes another image, and subtracts the two, and you find a bright spot. And in fact, if you zoom in, you can even see there's the galaxy, and there's our new spot, this supernova. And this is one of the furthest supernova ever discovered, something like 5 billion light years away, significantly further than what Kate can find, significantly further than what the Palomar Transient Factory finds. But this is about halfway across, over a third of the way across the visible universe. Here's 3 of the supernovae that HST has discovered, sort of the field that they're in, and then you can definitely see that one. This one's a little tougher, and then that's just a little blip, but that is a real supernova. And I said earlier, we can use supernovae to track the expansion history of the universe, getting into this whole runaway universe stuff that many of you have heard of. And so to talk about that, these are the supernovae that we use to do those observations. And I'll take a quick detour here to kind of get everybody up to speed on the expansion of the universe and Edwin Hubble. So Hubble, a very famous American astronomer. Of course, the Hubble Space Telescope is named after him. I love this picture because back in the good old days, you could have your pipe next to the telescope. They kind of frown on smoking near the telescope these days. All right. Anyway, so in 1929, he published a famous result, a very famous result, that all galaxies are moving away from each other, that the universe is expanding. All galaxies are moving away from each other. The sort of weird detail is it's the space between galaxies that's expanding. We're not all getting stretched at this moment in time. Kind of subtle, but I like to throw it up there because people ask about it sometimes. The other cool thing that he figured out was if you know the speed of the galaxy running away from you, you can calculate the distance. And we can measure speed by taking a spectrum. We can do this pretty well. And then we can straight up calculate the distance. So we can figure out how far away these galaxies are. So all galaxies are moving away from each other. This is the Hubble expansion. All galaxies have stars and dust, and so they weigh something. They have mass. And Newton told us a few hundred years ago that if something has mass, it's going to pull on everything else that has mass. This is the force of gravity. So you have galaxies running away from each other. They all have mass. They should start pulling on each other. And so until the late 90s, we thought, OK, all this pulling should slow down the expansion of the universe. We didn't know exactly how much. We didn't know exactly how many galaxies there were. But it should slow down. We had this expansion. Everything's pulling on each other. And then it slows down. Wonderful. So a couple of teams, two separate teams of international groups of astronomers used Hubble, found very far away supernova, tried to get their distances, and tried to measure how fast or how much the expansion was slowing down. And many of you know the punchline of this. In the late 90s, when they finally looked at the data and tried to figure out everything that could have possibly been wrong, they realized that the universe was actually expanding faster and faster. It was speeding up, accelerating in its expansion. And so it's not slowing down because of gravity. It's actually going faster and faster. There's something out there that is working against gravity, that's stronger than gravity on these huge scales of the universe, that we now call dark energy. And here's a pro tip for all of you in the audience. If an astronomer calls something dark something, it means we don't know what the hell it is. So most of the rest of my talk will be about dark energy, so keep that in the back of your mind. So we still don't understand what this dark energy is. We know a little bit about how it acts on the galaxies and how it accelerates, but there's still a lot of open questions. A lot of people think this is one of the biggest problems in modern science. This was a huge result. It was the science's breakthrough of the year in '98. And this is weird. This is totally bizarre. This is, you take your laser pointer, you throw it up in the air, and instead of coming back down, it starts zooming through the ceiling. That is unexpected. You should be weirded out by this fact. 15 years after the discovery, we're still trying to figure out what this dark energy is, how it affects the galaxies in the universe, and just what's going on here. Part of my PhD work actually was looking at a ton of supernovae from very nearby galaxies, trying to see if we could learn about the dark energy from those. The quick summary is we didn't learn very much. But I will point out that other people at other universities have different data sets doing similar analyses and got the same not very much answer as me. So that made us both feel better. I had a couple of email exchanges where I was like, I didn't get very interesting. And he was like, me too. So we're like, OK, good. Well, OK, so we need a new idea on how to look at these. But OK, that's cool. So this mysterious dark energy was very awesome in the late 90s. Science magazine thought it was very cool. Astronomers who weren't in the supernova field were like, I don't know. This seems to be sort of counter to things that we've known for 400 some odd years. So that's weird. And so a lot of other astronomers didn't really fully believe dark energy and the accelerating universe. Since then, in the past 15 years, other subfields of astronomy that are completely unrelated to supernova have confirmed the result, that it's there, that it's accelerating at basically the same amount, that has the same effect on galaxies. And so pretty much all astronomers do believe now that the universe's expansion is accelerating. If you want to chalk it up to dark energy or string theory or something crazy, that's a great open question that we can argue about. But the fact that the universe's expansion is getting faster and faster is pretty incontrovertible these days. And it's so incontrovertible that even the very conservative Nobel Committee awarded last year's Nobel Prize for the discovery of the accelerating expansion of the universe through observations of distant supernovae. Notice they don't use the words dark energy. That's still sort of an interpretation that's a little bit less clear. But the fact that that the universe's expansion is accelerating is the thing that people believe. Two teams sort of found it at the same time. A group led by Saul Perlmutter, who's in the physics department here and at the Berkeley lab, as well as another team led by Brian Schmidt, and his main student was Adam Rees, who wrote one of the seminal papers. Adam was actually a postdoc at Berkeley when he did this work. And as we heard before, Adam will be coming in October to give the Distinguished Sackler Lecture, which will be a little bit different than this talk, that's for sure. And he's a very interesting speaker, so I encourage you to do that, go to that if you're around in October. One thing I am contractually obligated to point out is that my advisor, Alex Filippenko, was the only guy on both teams. So I get paid this week because I said that to people. OK, so here is a video, a movie, that is sort of a cartoon representation of the expansion of the universe. So at the very beginning, we have the Big Bang. And then you see the universe expanding, and it is slowing down. For the first 5 billion years of the universe or so, it did slow down. And that was due to gravity, just like everyone expected. Then you see it sort of stop. If my computer was a little bit quicker, you wouldn't actually see it stop. But at some point, it starts to speed up. The expansion accelerates. It gets faster and faster. And that happened maybe 8 or 9 billion years ago. And that's when the dark energy, this acceleration, took over and started winning out over the gravity force, which had been slowing things down for a while. So there's that switch. All right, here's the composition of the universe. Dark energy makes up nearly 3/4 of the mass and energy in the universe. Nearly 1/4 is dark matter. Remember what I said about the word dark in astronomy. Very different than dark energy. They have very different observational characteristics. They have very different reasons why we postulated dark matter and dark energy. So they're very different. The only thing that makes them similar is the word dark, which you all know means we just don't really know what's going on. There's some great work being done around the world, especially based at Berkeley, looking for dark matter, trying to detect new particles that we've never seen before that might make up the dark matter. Yeah? So based on the supernovae, how the dark energy affects the universe, we can sort of count up galaxies and count up sort of the normal matter, which is a very small part. This intergalactic gas we can detect. And then we have observations of supernovae, of something called the cosmic microwave background, and sort of also how galaxies are clumped up on the sky and in the three-dimensional universe around us. And by combining all of those, you get some idea of how dense, how much matter there should be, the density of matter, how much energy total there should be, the density of energy. And then to get sort of the sub-chunks, you basically sort of add up to that amount, and you fill in the pie. So that's my like one-sentence description. You could easily give an entire hour lecture on this plot alone. Yeah? This is by mass/energy. Einstein told us E equals mc squared, so mass and energy are basically the same. They're off by a factor of the speed of light squared. So this is just straight amount of stuff, not divided by volume, really. Yeah, I think I'll stop talking about that there. So dark energy, nearly 3/4. Dark matter, nearly 1/4. Interstellar gas, sort of hot hydrogen floating around, intergalactic gas, sorry. Hot hydrogen floating between galaxies that glows in the X-rays usually, makes up about 3%. Then less than 1% is in stars and planets and other stuff. And of course, the vast majority of that 0.8% is in stars. A tiny, tiny fraction is in any kind of planet. And an even tinier, minuscule fraction is in us sitting in this room. So now that I've depressed you a little bit, the last couple things I want to talk about, and then we have some time for questions, is stars in our own galaxy that are going to go supernova. I mentioned earlier we expect about 1 per galaxy per century. We haven't seen one in sort of 400 or 500 years, so we're a little overdue. So there's a few stars around that are big and massive and we think are going to explode as supernovae. One of them is a very famous star called Betelgeuse, one of my favorite movies. In the constellation Orion, most people in the room, I'm sure, recognize. Here's good old Orion's belt, and then the sword, legs, arms, head. And so one of his shoulders is this big, bright red star, easily spotted in the winter sky, even from the middle of downtown San Francisco. It's pretty easy to spot, actually. And it's one of the biggest puffed up stars that we know of. Here's sort of the size of the star. And for comparison, Earth's orbit and Jupiter's orbit. So if you plunk this down where the sun is right now, it would immediately swallow the first like 5 planets. So that's pretty big. It's fairly massive, not crazy massive, maybe 20 times the mass of the sun, but it's very puffed up. Betelgeuse actually is Arabic for armpit of the giant. I like telling people that. And the other thing that's weird about these very massive and very puffed out stars is there aren't that many in the galaxy. There's not that many that we see. So they're hard to study. You've only got a few examples. And so we're really not sure how old this is. We're not sure what stage of its life it's at. And so it's hard to say exactly what day it's going to go supernova. We think it's going to go supernova in the next 1,000 years or so. There's some big uncertainties there, but 1,000 to a few thousand years is what we're thinking. But it's pretty unclear. When this goes supernova, this is a star bigger than 10 times the mass of the sun, so it's one of these things that's going to collapse on itself, bounce, and explode outward. It will not hurt Earth. It will not rip off our atmosphere and burn us all alive. It will probably be visible during the day, and will probably outshine the full moon, depending on what time of year and what months, and it'll probably be visible for weeks, months. It's not clear exactly how long, but it should be visible during the day. So this will be a very cool event. Maybe it'll happen tomorrow, maybe 1,000 years from now. I don't know. I wish I knew better. All right, another very famous star, and one that will go supernova in the near future, is Eta Carinae. This is in the southern constellation Carina, so we can't actually see it from California, unfortunately. This is an HST image, which shows a heck of a lot of stuff going on. So the star itself is actually buried way deep in the middle of these lobes. These two big bipolar lobes, a sort of curved hourglass peanut-looking thing, those are from an eruption in 1843. So in 1843, astronomers saw, oh, wow, this star got really bright. We sort of knew it was there and faint and boring, but then it got really bright and then faded away. And they're like, maybe that's a supernova, maybe it's a nova. This is more like a classical nova that I mentioned at the very beginning of the talk, but it had some outburst. It got very bright. And then we go back just under 100 years later, and we see these big lobes. So this is the junk that was blasted off in 1843. Now you have all this red junk around here, the much more diffuse, wider stuff. And that actually, we think, was something like thousands of years ago, tens of thousands of years ago, that there was another outburst. And that's what the material looks like 10,000 years ago. So maybe another kind of baby nova remnant kind of thing. Eta Car is about 8,000 light years away, so not super far away, definitely in our own galaxy. It's much further than Betelgeuse, but it's actually much bigger than Betelgeuse. It weighs maybe 100 or 150 times the mass of the sun. This is one of the most massive stars that we've ever seen. And so when this thing goes supernova, we could have maybe a couple of little issues. The last thing, or one of the things I want to point out is the size of the solar system is about one of the little clumps in here, one of these tiny little features. That's about the size of the entire solar system. So this is a massive thing on the sky. So we're not sure when this is going to explode. Like I said, we only have a few examples of really massive stars. We're not sure about how old it is, what stage of its evolution it is. We're thinking sort of anywhere from a few years to a few million years. So big error bars. That's the best I can do, I'm sorry. So this will explode again as one of these massive stars collapsing, bouncing off the iron core and exploding outward. Probably won't hurt the Earth as far as burning the atmosphere or anything like that. But there is a pretty good chance that there'll be some radiation or high energy particle issues outside of the Earth's protective magnetic field. So if we have a moon base or astronauts orbiting or GPS satellites, stuff like that, when this goes off, we're going to need to make sure that they're well shielded from these high energy particles. Otherwise, you turn into the Fantastic Four or something like that. But it will not burn off the atmosphere. It won't kill us. If you're on the ground, if you're under the protective magnetic field of the Earth, you're probably OK. That's what we think. OK, and then I will just conclude real quick why we would not be here without supernovae, why they're interesting. The supernova can push the limits of our understanding of many different astrophysical topics. They can trigger star formation, new stars being born, and of course, the planets around those stars. They create and release the elements that go into us, rocky planets. Famous American astronomer Carl Sagan used to say we are all made of star stuff. It sounds very nice and hippie, but it's literally true. The calcium in our bones, the oxygen we breathe, the iron in our blood was all cooked up in a star. It all exploded outward in a supernova and then got incorporated into the sun and then the Earth and then us. And I talked a little bit about tracking the expansion history of the universe. Supernova observations led to the discovery of the accelerating universe, the runaway universe, and dark energy. And really many scientists, physicists, astronomers, and maybe even some biologists believe that dark energy is one of the biggest mysteries in modern astrophysics and in modern science. And so we're working hard to figure out what it is, to get more information about it, where it comes from. Everybody's got their pet idea of where dark energy comes from. And I will stop there and take questions. Thank you.
You said that the supernova dark matter. Dark matter originally came from the rotating galaxies. So is there something I'm missing there?
So the original impetus to have dark matter out there is from the rotation of stars within galaxies. That's correct. The question was, did supernova help lead to the discovery of dark matter and dark energy? Dark energy, yes. That's why we came up with dark energy, was to explain the supernova observations. The dark matter was sort of come up with to explain the rotation of stars within galaxies. Using observations of supernova, you can get the percentages of each of those, the dark matter, dark energy, and regular particles, in addition to using observations of other stuff. So originally dark matter was proposed because of the galaxy stuff, like you mentioned, but to get the relative percentages of how much is in the total universe, we use a little bit of that, and also the supernova come into play, because you kind of got to add up to the whole pie. Back there.
How do you ascertain some of these analogies you guys, with the spectrum thing, misrepresented by Doppler effect?
So in fact, they are not only misrepresented by Doppler effects, they are intimately linked with Doppler effects. So the Doppler effect is when you hear a train coming towards you, it sounds one way, and when it's zooming away, it sounds another way, or European sirens. We can do the same thing with light. Light's wavelength, just like the sound of those sirens, will change if it's coming towards us or going away from us. And so we can use that shift to figure out how far away the galaxy is. We can also use that shift to figure out how fast the material is exploding away in the star. And so all the spectra I showed, or the two spectra I showed, and all the spectra I've ever looked at, the thousands of spectra I've looked at, are all intimately linked with that Doppler shift. And if I don't account accurately for it, then I could get things wrong. But we think that we're accounting accurately. It's all self-consistent, right? All the material should be basically moving around the same speed. You shouldn't have something moving 1 mile an hour and something moving 1,000 miles an hour. They're all around the same speed. So we do have to take that into account. If you don't, you will get the wrong answer. But we do take that into account. Yeah?
Given the rate of the expanding universe, how long until the sky is black?
Great question. So given the accelerating universe's rate, how long until the sky is black? It's not totally clear. We think that the dark energy, the accelerating expansion, will affect sort of groups of galaxies, pulling them away from each other. But it's not completely obvious that the nearby neighbor galaxies of ours will also get completely ripped away. If they do, if it, we still have error bars, it's not totally clear. We're talking hundreds of billions of years before something like that would happen. Andromeda galaxy is going to crash into the Milky Way in 5 billion years. The sun's going to burn out in 5 billion years. We have lots of other things to worry about. But if you are still around, there is a chance that sort of 100 or a few hundred billion years in the future, things might get pretty dark. But again, the stars in our own galaxy will most likely be still there. Some of the nearest galaxies will most likely still be there. So if you go out at night, it probably wouldn't look that different as far as that goes. Yeah.
Could you say a word about, I don't know how to pronounce it, but
Eta Carinae, yeah.
Why there's that bipolarity?
That's a great question. So I will go back. So this crazy peanut shape, we think that is indicative that it has a binary companion. We think that we have two stars going around each other, and so when you have an outburst, you're actually going to blow stuff out sort of along the axis that you're rotating around. And then as the things spin around each other, they orbit around each other, it sort of constricts the material that can escape that way. So that's the running theory. There's a couple of other pieces of evidence that there's actually a second star in there. Not nearly as massive, not really doing too much, just kind of along for the ride, and will probably get pretty messed up when this thing explodes. But that's sort of the idea. There's still some other possibilities, but that's the one that people like the most, I think. Over here.
Yeah, could you explain the differences between the three spectrums, the continuous, emission, and absorption?
Sure. So the basic, I put that up there just to sort of give people a bit of an idea of what these could look like. But the basic idea is you have, emission, you have light, you have brightness at a bunch of different wavelengths. And so sort of the three most basic things are, it's the same at every color, which is a continuous, nice, constant line. It's either, well, it could be totally black, but that's not very interesting for me. Or it could have very specific emissions. So these lines I know are from hydrogen, because as I said, every element has very specific wavelengths that it is bright at, like a fingerprint. And so this is a hydrogen emission spectrum. Anytime I see these four lines together, that's hydrogen. Similarly, if I see the absorption, I know hydrogen's around. And so sometimes in certain configurations, you can get mostly dark but bright spots at these lines. And then you can also get the opposite. You can get mostly bright with dark spots at these lines. And that's just that's based on the physics of what's producing the light, what's in between you and what's producing the light.
The sun itself is giving the top one, right?
So technically, the sun itself gives us absorption lines, but they're so skinny and small you would never see them by eye in a rainbow. But you're right, by eye in a rainbow, absolutely we get the continuous spectrum. If you have the spectrograph in a telescope, you'll actually see little absorption lines in the sun's spectrum. So hopefully that clarifies a little bit. All right, cool. Yeah, right.
2004, I think it was December, there was a magnetar that blew up at the other end of our galaxy, and the effect of it, affected some of the satellites in orbit. And it's kind of, I remember reading an article and somebody was making a point that something that far away, an event that far away, still kind of tapped us on the shoulder. I mean, if that thing would have been closer to us, I mean, is there any other things that we, not maybe worry about, but have maybe concern that an event like that could strip off our atmosphere?
So there are sort of relatives of supernova called gamma ray bursts, which are a bit higher energy and are more focused, and so more focused like a laser beam. And so if one of those are pointing at Earth, much further away, sort of other side of the galaxy, could do some damage. We know of many stars that could become a gamma ray burst. We don't think that they're pointing at us, though. So we think that that'll be okay. It's not totally clear. There's not as much. It's a younger field. There hasn't been as much work done on it, and I'm not an expert in that subfield, but we don't think anything's pointing at us, so we're okay with that. It is much more likely we're going to get hit by an asteroid, so go worry about that when you go to sleep tonight. Right here.
You mentioned that stars like Betelgeuse are relatively rare.
Mm-hmm.
Why is that? And do we know anything if they have planets orbiting them or anything like that?
So the question was, I mentioned that Betelgeuse and sort of massive stars in general are rare. Why is that, and do they have planets around them? They're rare because we think it's hard to make very massive stars. When you have these clumps of gas collapsing and you get stars being born, we have a pretty good idea of the distribution of how many little guys you get, how many medium guys you get, and how many big guys you get. And we just don't think that big ones form that often, and it's tough to form them. And the details of why it's tough are a little bit beyond what I want to talk about and a little bit beyond what we know. People are still running simulations trying to figure out why that's what it is. But we can go out and count the stars that we see and get this distribution. We recover most of what we expected. But the big ones are rare, and we're not totally clear why. But it is hard to make for a couple of reasons. As far as planets go, massive stars don't live long. The more massive a star is, the shorter its lifetime. And so with our models of how you form planets, it takes a while. So there's a good chance there's just not enough time before the big stars go supernova to even form a planet. So it's pretty unlikely. I don't know of any really massive stars that have had planets found around them, and I think we don't expect that. But I'm not totally clear. I'm not a planets guy. There's lots of planets guys around here. Let's go right here. Mm-hmm.
Has had smaller novas in the past.
Mm-hmm.
Is that typical that a star will have little novas and then go supernova?
Yes, for the most part, and in fact there's a class of these novas called recurrent nova, in fact, specifically because we know they sort of do this over and over. Eta Car is not really a nova, just to clarify. It's similar in that there's a little outburst. It's a luminous blue variable and various bursty things. But we think massive stars go through these sort of death gurgle burps of outbursts, and then we think that the white dwarfs, the type 1a supernova white dwarfs might, when you're adding mass from the companion, they might kind of flare up and do these little novas as well before they actually completely go supernova, before they hit that magic limit. Same thing with the massive stars. They might have these death gurgles before they really lose all their, they have an iron core and collapse on themselves. And there's been observations for Eta Car, there's been observations for a couple other supernova of pre-explosion outbursts. It did some crazy outbursty thing and then totally blew itself apart a few years later, or 100 years later, or decades later. So yeah, we think that happens in a lot of cases, but they're so much fainter, they're often very hard to see unless they're really close. So that's part of it. Let's go here. Yeah?
You mentioned that you can't fuse iron in a star.
Correct.
Because it's endothermic.
Right, it takes an energy to fuse iron, yeah.
What massive star would be required to fuse iron?
It can't happen because you would never get the amount of energy there before it collapses on itself as a supernova. You just can't do it because once you build up enough iron to get, you need extra energy to make that happen, which happens in the supernova itself. But well before you got there, there would be no support for the outer layers and it would have to collapse and explode. Way in the back. So the question was, can dark matter or dark energy be an extension of regular matter? The dark energy is really not a particle. It's some kind of energy field, is the fancy Star Trek sounding word for it. So we definitely think that that's something different that we don't understand yet. The dark matter is particles. We've done some surveys, other astronomers, not myself, have done surveys to try and see what is the dark matter, what could it be made of. And a very small percentage, maybe a few percent, is probably just regular matter that's not very bright. It literally is just regular matter that is dark. The vast majority of the dark matter very much seems to be new particles that we don't know about yet. And it's those new particles where if you want to say it's an extension of regular matter or some new physics or something, that's kind of up to you because we just don't know yet. Yeah?
What's the, can you speak a few words on the transparency of dark energy and or dark matter? They're not at all transparent how much stuff out there.
So can we see through dark matter or dark energy? The dark matter is as transparent, we think, as everything else. The way we found dark matter or first proposed it was through the gravity force. So dark matter doesn't glow, we can't see it with a telescope, but we can see its gravitational effect on normal stuff that we can see. And so it's out there, it doesn't really block light, just like most of the stuff doesn't really block light, but we can detect it gravitationally. So that's transparent in one way of thinking about it. The dark energy seems to permeate all of space throughout the entire universe. It's all out there. And we see the cosmic microwave background, which is sort of the relic of the Big Bang. That's one of the furthest things that we can see. And the dark energy detections are well before that. So we can certainly see through it in that kind of sense. We can see things that are further away than where we know dark energy is. So in that sense, it would be, I guess, considered transparent. Straight back.
I know it hasn't been quite confirmed yet, but it's pretty much certain that the Higgs boson existed.
Mm-hmm.
How has that affected the list of possibilities for candidates for dark matter?
Good question. I'm surprised it took that long to get a Higgs boson question, honestly. The standard model of physics, and again, particle physics, that was one of my worst classes in college, but the standard model has sort of been thinking that that was there for a while. It was sort of expected to be there, and so it was good that the people at the LHC sort of found it where we sort of figured it would be, so that was useful, and didn't really change things too much as far as dark matter or even dark energy type stuff. The thing that's interesting going forward, one of the best quotes I saw from one of the CERN physicists was, it's good that we found it sort of where we expected it, but the tiny deviations that we will better characterize in the next few years is what's going to figure out new physics. That's what's going to get us to new stuff. Is, okay, we expected 125 giga-electron volts, but it's 125.6. Whoa, where'd that 0.6 come from? What does that mean? And that, I think, is where the new physics is going to come from the Higgs boson work. And very well could lead back to possibilities of dark matter, probably not dark energy, but certainly remains to be seen. And that kind of cross-physics collaboration between astronomers and particle physicists is good and something that hasn't happened much in the last 100 years or so. Yeah, right down here.
So I think there was one of these talks focused on dark matter where somebody showed colliding galaxies, and then apparently the dark matter passed through the collision, and they could use the gravitational lensing of the dark matter to show that it had separated from the visible matter. I wonder if you heard about that result, and if it shed any light on dark matter?
It supported dark matter's existence. So this was a couple of observations. There was an original one many years ago, and then a few in the recent past of galaxies merging, colliding, kind of going past each other, and the way that the luminous matter, the stars and gas that we normally see, interact is what we see, but then we can also calculate their orbits, and that's all gravity, and so the dark matter that's there will tell us about those orbits, and so we can use that as yet another way to say that, yes, there's a lot of dark matter in these galaxies that's stretching stuff out in ways that we wouldn't naively expect if we just took a picture and said, here's all the gas, here's all the stars. Yeah?
The rate of expansion of the universe is accelerating. Would it at some point reach the speed of light? And if so, what would that be?
Very good. I get this occasionally, and I always fear this question because it's always hard to answer. So that was one of the reasons I threw in that caveat when talking about Hubble expansion of it's the space between galaxies that's doing this expansion and this acceleration. So if you pick sort of, Earth as a reference frame, we've seen supernovae that are moving nearly like 0.8 times the speed of light, I think is what I calculated. But it's this weird relativity issue, so the space between galaxies can definitely go faster than the speed of light, no problem. It's the stuff within that fabric of space-time, very fuzzy word or term, that can't go faster than light. And so it's a subtlety of relativity and the Hubble expansion. And that's basically the end of my understanding, to be quite honest. That's usually where I cut it off and pick a different question. But that is a very good question, yes.
So along that line,
Man.
center.
No.
There is no center.
The center is everywhere.
Expanding. I don't have the concept of expansion if there's no center to move away from.
Because everything in the universe is expanding from all places at all times. You can pick an arbitrary center, and that's fine. Everything's moving away from that center, but you can go anywhere else in the universe, and that can be your center. Because all expansion is going. I don't have the demo, but one demo that maybe will help. If you think about a balloon, and I put a bunch of pennies on the balloon and blow it up, that's expanding, but you can only live on the balloon, so where's the center? It's not inside the balloon. You can't do that. You're on the edge of the balloon. So it's not a great analogy, and it'd be better if I had it, but yeah.
Are parts expanding at different rates, or if not, how do you have the Andromeda and Milky Way crashing into each other?
Good question. So the universe's expansion is on the biggest scales. The dark energy is accelerating us on the largest scales. But if you get closer and closer, then other forces could win. And so in Andromeda and the Milky Way galaxy, gravity is actually much stronger than dark energy. And so that's winning the net force game and is pulling the two together. That's why I was saying that the sky very well might not get dark, because the galaxies right near us are being pulled by gravity, and that's stronger than the dark energy.
At what level then? Is that the supercluster level?
We're talking about, somewhere between galaxy cluster and supercluster. And again, we don't know the dark energy strength well enough to say exactly like, here is the bubble where, gravity will win, and outside of that, dark energy will win. We have a good idea about when in time it took over on a universe-wide scale from observations of supernova like that video I showed. But as far as, the nearest 5 galaxies, we think gravity's winning and they're going to stick by us forever. Yeah?
Related to the question before, if we are analogous to the surface of the moon in its expansion, does that mean that the universe is expanding in 4-dimensional space?
Yeah, space-time. 3 dimensions, up, down, left, right, back, forth, and time. That is 4 dimensions. So however else you want to think about that sounds great, but that's sort of what I have in my head. And
Not 4-dimensional space.
Nope, 4-dimensional space-time. The balloon is an analogy of 2 dimensions and time. So it's not quite accurate, but it's hard to make a 4-dimensional space-time balloon. Although it's on my to-do list, but we can work on it in the garage. Yeah. Also a good question. The answer is physics doesn't tell us, so everything and nothing. The question was, what is the universe expanding into? Since by definition, according to physics and astronomy, the universe is everything, it's not expanding into anything. It's everything expanding, which I know is a horrible answer. I'm sorry.
What about the recent mathematical theories about using fractals and explaining complex planes in terms of expanding out? It's more just, it's not really expanding out 3-dimensionally, it's more kind of wrapping inside, folding inside itself.
So the question was about using fractals and higher order mathematics. This also gets into string theory. There's a lot of string theory ideas that you have extra dimensions beyond our 3 dimensions of space and then 1 of time that are wrapped up or wrapping around the universe. Those are all really great stories. If they make a testable prediction that I could go look at with a telescope, that would be awesome, and I would be more than happy to try it. But currently, pretty much all of these string theory and higher level math and fractal ideas do have lovely equations and are very elegant and can explain some of our observations, but they don't make new testable things that we can go out and actually look for. And when they do, it'll be great, and we'll definitely try it. Yeah?
Why do astronomers think that dark matter is particles rather than a flaw in the theory?
There is a subset of astronomers that think that perhaps we don't understand gravity on the biggest scales of the universe, and perhaps that's leading to what we're calling dark energy or dark matter. That's certainly possible. But the problem with any of those so far is you have to tweak the equations of gravity so finely that it seems very, very convoluted, that you have to add in all these extra special terms where in this regime of distance this matters, and in this regime of distance this matters, whereas dark energy, as proposed by actually Einstein originally, you just add in one constant. That is one constant accelerating force, and that actually seems to work with all of our data. So it's more elegant, so from a Occam's razor argument, which may not be the best way to go, that seems to be what we're doing right now. There's actually already been a few of these modified gravity theories that have been disproven by more accurate supernova observations and further away supernova observations. But there's still some that are valid, and there's plenty of astronomers that think that might be an explanation for these, and it's still not clear. That's why I said, the Nobel Committee didn't award it for dark energy. They awarded it for the acceleration, which has to be explained by something. Perhaps different kinds of gravity, perhaps dark energy, accelerating universe, or cosmological constant is what it's called sometimes. Yeah?
So you're saying that the individual components of galaxies are not expanding, but the galaxy structures themselves are expanding.
Nope.
And on the unbounded or bounded universe, right? So where does the empty space come from if it's bounded? And where does it go on forever?
We think the universe is probably infinite. The visible universe is definitely not infinite. The space between galaxies is just expanding and stretching itself, and we think that it can expand and stretch itself to infinity. So that's how we get the space from the space. Man, you guys are really on this stuff. This is awesome. Really pushing me today.
Maybe one more question.
Okay, one more question sounds good, and I can hang out for a few minutes, but I actually have some good friends to meet afterwards. Yeah.
What kind of observations do you think we'll get with the James Webb telescope?
That's a great question. What kind of observations will we get with the James Webb telescope, sort of the successor to the Hubble Space Telescope? It'll be bigger and better and much more expensive. But it will hopefully fly in a few years and it'll be really awesome. We will see even further supernova, that's for sure, which will be interesting. We can do better on dark energy and quantifying the dark energy itself at even further distances. It'll do really good at looking into clouds where there are young stars being born. Possibly also stuff like Eta Carina, where we have very dusty clouds around big stars that are dying. It should be able to look into those very, very precisely, measure very small distances between things. So the higher resolution, the ability to see smaller distances between things, I think will be a huge thing for that telescope. Honestly, I have been not thinking about what I could do with the Webb telescope because it's a few years off, but that is a good question, yeah. Okay, so I think we'll cut it off there, and thank you.
It's the next Science at Cal lecture. Our speaker will be Dr. Anton Trenzen. He is with the Experimental Astrophysics Group at Space Sciences Laboratory, and I wrote down the title of his talk because it's a good one. Can one see a flower through a granite wall? Amazing capabilities of neutron imaging. So mark your calendar for that one. And later in the fall, October 3rd, we're already putting the word out that Nobel Prize-winning physicist Adam Rees of Johns Hopkins University will deliver the Distinguished Lecture in Astronomy. That will be in the Bechtel Engineering Center, and of course we'll be announcing it as the date draws closer. And of course, his topic will be how supernova reveal the accelerating universe. But we don't have to wait for October, because as you know, today's lecture, which will be delivered by Dr. Jeffrey Silverman, is going to inform us about these exploding stars and the runaway universe. And dark energy and the runaway universe. So the good news is that we have Jeff with us here today. He will be leaving Berkeley soon to assume a postdoctoral position at the University of Texas at Austin. He's been studying and observing supernova here with Professor Alex Filippenko, and we're very lucky to have him. So please join me in welcoming Dr. Jeffrey Silverman.
All right, good morning, everyone.
Hello, everybody. I'm Rachel Winheld, and on behalf of Science at Cal, it's my great pleasure to welcome all of you to the Science at Cal lecture today. always great to see familiar faces, and we have a lot of new people here in today's audience. So welcome to all of you. I know we have some students from visiting the Berkeley campus this summer to study computer science from high schools all across the U.S., and we're really thrilled that you could join us here today. And I know that one of my colleagues in the physics department is bringing some young members of her family to the talk today. So everybody, welcome to today's lecture. If you are new to this lecture series, or you're not yet on the Science at Cal e-list, but would like to stay informed with occasional notifications about this lecture series and other activities going on through Science at Cal, please go to our website, scienceatcal.berkeley.edu. I welcome you to visit the site and sign up for the list. I also like to mention that while you're there, you can click on Support Science at Cal, and if you're so inclined, large or small donations from people like you are incredibly important to us to help us maintain and grow our programs, as well as let our administrators and our science policymakers know that you value this kind of opportunity. So just a couple of announcements before we get to today's talk. If you're going to be around in August 18th.
And thank you, Rachel, for that very lovely introduction. So, as Rachel said, I'll be talking about exploding stars, known as supernovae, dark energy, and the Runaway universe. I've been here for almost 7 years now, working with Alex Filippenko. Many of you might recognize him. He's on TV a lot. Here's us from graduation last year. If you watch The Universe on the History Channel, he's in there a lot, and I'm in the background in a few episodes. So there's my plug for my TV career. Okay, so what is a supernova? Let's start off with some basics, folks. The plural is supernovae, sort of a Latin bastardization. I'll sort of switch between the two. They're bright and powerful explosions of a star, the death of a star. Some of the biggest explosions in the universe. The speed of the material exploded outward can reach something like 20% the speed of light, the speed of light being the fastest speed in the universe. A single star exploding can outshine its host galaxy, which is made of hundreds of billions of stars. And in about 1 month, one of these supernovae can emit as much energy as the entire sun will in its 10 billion year lifetime. So the name nova is Latin for new. I don't know much Latin, but I at least know that one. It was first used by some of the Renaissance astronomers to describe new stars that popped up in the night sky. The prefix super, we sort of added on in the 20s to distinguish them from what we now call classical novae, sort of smaller, weaker cousins of the supernovae that I'll talk about. So I won't talk about classical novae today. I'll talk pretty much all about supernovae. Whether or not humans knew it, we have been observing supernovae for about 2,000 years. I'll show some historical records of people seeing supernova, not knowing what they were until maybe about 100 years ago, but seeing them and pointing them out for the last couple of millennia. And the term supernova was coined by a Swiss. This is a petroglyph from New Mexico. The Anasazi Indians made this in the year 1054. And sure enough, if you go to New Mexico and you look this direction and you take a look and you figure out when we think the supernova went off, here's a picture of the supernova. Here's the moon's relative position and the phase, so it was a nice little setting crescent there. And then the artist put his hand up there to sort of give you a size scale to figure out what the distances between these two are. And that seems to be correct. We're pretty sure that this is a petroglyph of the 1054 supernova that gave us today the Crab Nebula. Luckily, we've come a little bit forward in technology in the last 1,000 years. It would be hard to write a supernova thesis if all I had was rock drawings. It would also be a much heavier book. My thesis is already pretty heavy, but... Okay, so skipping ahead a few hundred years to another interesting character in the history of astronomy, Tycho Brahe, famous Danish astronomer, observational astronomer, basically with just his eyes. He found a supernova in 1572. Sort of, again, just cataloging all the stars out there, and then saw a new supernova, or a new star appear in the night sky. This guy has a lot of quirky stories about him. My favorite one I like to tell is he was apparently a hothead, and in college he got into a lot of fights and duels, and in one duel he got his nose cut off. But he was wealthy enough and was endowed by the local princes enough where he got a gold and copper plated nose put in. Either this was probably before this painting was made, but I assume he paid the painter enough to make him look pretty. So Yeah, interesting character. And here's what Tycho's supernova looks like today, about 500 years later. Again, we have a supernova remnant where there's gas and material running into sort of the surrounding ambient medium around the star that exploded. This is actually an X-ray picture. This is not the visible light we see with our eyes. These are X-rays. This astronomer named Fritz Zwicky, he worked at Caltech for most of his career. He was sort of a funny, curmudgeonly-looking guy. He was known to call people spherical bastards because they were bastards any way you looked at them. Sort of one of the people I model parts of my personality after, if anybody of you know me. Okay, so onto some pretty astronomy pictures. Any good astronomy talk should have lots of pretty pictures in it. So this, as many of the amateur observers in the crowd know, is the famous Crab Nebula. This is a picture using the Hubble Space Telescope. And so when a star explodes, it gives off a lot of energy, a lot of material gets blasted away from the star. And when that material from the exploding star runs into the gas and dust that was sort of just minding its own business sitting around the star before it exploded, it heats up. And when gas in space heats up, it starts to glow. And so this is from a supernova that went off in the year 1054, so almost 1,000 years ago. And what we're seeing here in the modern day is the gas and material that blew away from that star running into the surrounding material. And when that crash happens and it lights up, we call it a supernova remnant. So I'm starting sort of at the end of the supernova. After it's been exploded, after about 1,000 years or so, we'll see this remnant. And so I said the supernova went off in the year 1054, and it was recorded by everybody that was in the northern hemisphere that was looking at the sky, from Asia, North America, parts of Europe, but they had some dark age kind of issues at the time, but we think there might be some records there. But pretty much around the world, people saw this. It was bright enough to see in the daytime for almost a month. So a brand new star that was bright enough to see during the day for almost a month. That was really freaky to a lot of people back then. It'd be really freaky to us now, for the most part. And it was visible well before the telescope was invented. So by just the naked eye at night, it was visible for nearly 2 years. So here is one of the earliest records, perhaps the earliest record of a supernova.